SwayamPrabha. Digital India. Educated India.
Hello and welcome everyone to today's lecture in this series for the modeling of multiphysics system. So in this segment we have been continuing on towards discussing solid mechanics as our physics. We have already covered heat and mass transfer in the former couple of lectures. So in the last two lectures in solid mechanics, so as you can see from the title that it is solid mechanics 3. So in the last two lectures, we have covered two segments of modeling of problem based upon solid mechanics. So the first lecture it covered the relation between deformation and strain. The second lecture we looked at different types of stresses and how forces and stresses are related to each other. So up to the last lecture, we came up to the point of force equilibrium. Right. So we have seen how a tangible deformation can be related to different definitions of strain. These strains can be based upon the initial frame of reference, that is your Lagrangian strain, or the final frame of reference, that is your Eulerian strain. Likewise, we have stresses which translate the force divided by the area, that's the traction vector, in all three directions. So our stresses, that is internal resistance to deformation, was also defined based upon our coordinate frame. So if we had the final force or the force applied divided by the deformed area, then it was a Cauchy stress tensor. If we had the final force or the applied force at that time divided by the undeformed area, then it was called the nominal stress. And then if you had a projection of the final force onto the initial frame of reference and applied on the undeformed area, then it was called the material stress. So Pk1, Pk2. All right. Then we have moved on towards force equilibrium, that is a conservation of momentum. We will be conserving both linear momentum and angular momentum. So in this case, so consider a solid body that is deformed under the external load by forces. This is our expression that we will eventually come up by the conservation of linear momentum. Okay, so it's by the conservation of linear momentum. We will start this problem by our definition of forces. So we had talked in the last lecture about two types of forces. One was a surface force and a body force. So we had a diagram in which our initial body got deformed, and we had seen that there were some body forces acting, B vector, and then some surface forces acting on the surface, that is our traction vector. Okay, so this was our initial body and our coordinates E1 and E2. Okay, so we were looking at two types of forces. Our surface force, P vector due to surface force, was an integral over the surface area A into T vector of dA, and our body force was equals to integral over volume V, density times the body force vector per unit weight into dV. Okay, so we had seen that T was our traction vector. I am just giving a small revision, which was n vector into sigma, where sigma is our stress tensor, in this case a Cauchy stress tensor, and B is our body force vector, which is per unit mass, the weight of the body. So the net force P of I, let us write in terms of index notation, will be equals to integral over area A, T of I into dA, plus integral over volume V, rho B of I into dV. Okay, so this was the expression that we came up in the last lecture for our net forces and the force balance. Right. Okay, now we have three terms, right? We have this force term on the left, we have the surface driven forces on the right, the first term, then this body force driven term on the second term, that is our rho bi term. Okay, let's treat one at a time. So we can take this pi, our linear momentum. So the linear momentum for the body can be defined, say, by a term L of I, it is a vector, which is equals to integral over volume density times the velocity of I into dV. Okay, so this is a linear momentum, mass times velocity, mass is density into volume. The force is the derivative of the linear momentum with respect to time. So, P of I is equals to d by dt integral over volume V of this rho Vi to dV. So, we can take this derivative inside the integral. If density is not changing with time, then we can say this is integral over volume V rho dVi by dt into integral over volume V. This derivative of velocity with time is acceleration, as we know very well, is rho ai to dv. Okay. We also know that the traction vector T of I, so the traction vector equals to Nj sigma ji. If we replace everything back into our equation, so our governing equation becomes let us write this first, our RHS term, integral over area A sigma ji Nj dA plus integral over volume V rho bi dV is integral over volume B rho ai dV. Okay. All right. So, we are progressing towards something which looks very similar to we have solved heat diffusion equation before. So, right. So, these kinds of expression now we are very familiar with. When what we need to do is we need to convert the area integral to a volume integral. Okay, and this we need, how do we do this? We use Gauss divergence theorem. So, integral over A, we had this sigma ji Nj dA will become integral over volume V del sigma ji over del xj, the gradient of the stress tensor, to dV. This term, so it is just the divergence of the sigma, del dot sigma. Okay. So, we substitute this, substituting into the governing equation. We will have integral over volume V. We can take all the volumetric integrals into one term and just let us club it together to save some time. So, it is del sigma ji del xj plus rho bi minus rho ai dV is equals to 0. Again, for any arbitrary volume, we can say that the integrand is 0, because every point within that arbitrary volume, this equation should be satisfied or should justify. Okay. So, if that is the case, then del sigma ji equals to del xj plus rho of bi minus rho of ai is equals to 0, or del sigma ji by del xj plus rho of bi equals to rho of ai, and ai is also in terms of our initial deformation or displacement is del squared ui by del t square. Okay, now this equation is our conservation law. We have seen that the gradient of the divergence of the stress tensor added with this body force term is equals to density times acceleration, and the acceleration is the second order derivative of our displacement with respect to time. Okay, now we have on the left hand side we have a term which is driven by the stress and the body forces, and the right hand side we have a term that is driven by the displacement. So, that is where the importance of today's lecture would come, is that we need a correlation or an equation that can relate the stress to the displacement or to the strain. We already know the relation between strain and displacement. So, if we can relate the stress to strain, we will be able to relate the strain to displacement, and we can have one equation in which we can get rid of this stress term, and we will have just an equation based upon the displacement or the strain. Again, Bi is body force, we do not need to replace it with any other term. Body force can be gravitational force, it can be due to some electromagnetic effects in the body, but it affects the entire body, and we typically know the value or know the vector for this case. Sigma ij is, on the other hand, we do not know. There is no way to determine what sigma ij is. It is internal resistance to that deformation. Okay, so let's write it down in terms of divergence. So that is vectorial notation is del dot sigma plus rho b vector is equals to rho del square u vector by del t square. So this is our equation or expression, which is our conservation equation or governing equation. So we will refer to this in the upcoming segment. So we need to replace this sigma with strain, which is a function of the displacement. So we are replacing the stress with the strain, and the strain is related to the displacement. So we can have one equation of displacement, and that will be our Navier's equation. All right. If it is clear so far, then we just look at the other stress measures. So we have also looked at three other stresses. So we had this Kirchhoff stress, when we have our nominal stress and our material stress. So we will see how those fit in to this. So Kirchhoff stress itself has no physical significance, and the material stress are important. So the other stress measures we will have in terms of Sij, that is our pk1, pure Kirchhoff 1, or the nominal stress, del xi plus rho naught bj. Okay, so what did we do? We have introduced this rho naught, so undeformed density, and if we replace S with sigma, then it is del of sigma ik f jk del xi plus rho naught, the rest is the same. Okay, so this is with respect to our nominal stress, pk1 stress, and this is with respect to our material stress or pk2 stress. All right. So we can express our governing equation in terms of any of these stress measures. We have also seen that for infinitesimal deformation, all the stress measures are the same. So in most of the applications, we do not really care what kind of stress measure we are using. However, in some special cases where you can have very long stretches or the body deforms plastically or has some elastomeric behavior, in those cases we would need to consider each of these definitions separately based upon our frame of reference. So we will also find out how they are related to the strain, that is a Lagrangian strain and the Eulerian strain, and using the constitutive models. Okay, one thing to note in this case is that these equations are a set of 3, one along each direction. Okay, so if you look back again, you can see that I is the unrepeated index. So you can have these equations in all 3 directions. So let me just write in one direction, for example, in this one. So del sigma by del x1 okay. So this is along E1 direction. It's along E1 direction. One thing I did, just you notice that this sigma ij, ji is equals to sigma ij, because this, the Cauchy stress tensor is symmetric. So we can use this symmetry of the Cauchy stress tensor for converting the sigma gi to sigma ij. That's what I did over here. I just replaced the ij with gi. So please do not get confused regarding the same. Okay. Now we have individually defined strains and deformations. We have defined stresses and forces. We have also expressed a conservation equation which can relate, which can satisfy the conservation of linear momentum. I have not written up the expression for the conservation of angular momentum. It is just a cross product of xj with respect to the tau, or the xj with respect to the rho b term. Okay, so x vector crossed with rho b, or x vector crossed with the t term, that is a traction vector. So you could, so that you can try it out on your own. If you are having some difficulty, then you can always refer to the Alan Bauer's applied solid mechanics book, and check out the derivation. Okay. Now from this we have come up that we need an expression which can relate the sigma to the strain or to the displacement. So there is a requirement from the conservation equation, or the governing equation. There is a need to relate the stress with the strain or the displacement. So if you want to relate the stress to the strain or the displacement, in that case we are looking for another set of equations or models, and these are called the constitutive models. So by definition, the constitutive model for a material, and this is material driven, is a set of equations which relates the stress state of a body to the strain. It can also relate to the strain history, strain rate, or other behavior rather. Okay, so it is a set of relations which can relate the stress to strain rate, stress to strain history, depending upon the type of material. Some material, for example, linear elastic material, it will be related, we relate the stress to strain. If we have some viscoelasticity or some plasticity, then we also have to consider the strain history. In the case of certain flowing polymers, we can also consider the strain rate has an effect. So it's both the strain and the strain rate has an effect, because there is some fluid component and some solid component in that case. So the model needs to constitute both applications. So it is just not stress and strain, it will also include the other parameters, or may include the other parameters. Okay, with that in consideration, this equation, these constitutive models differ from from the governing equation, from the conservation law, as these cannot be derived from fundamental physics, but rather fitted against experiments. Okay. So, these expressions or these constitutive models, unlike the conservation equation in which we saw that how Newton's second law was used to develop that expression, the constitutive models cannot be determined by these fundamental physics. However, these can be determined by fitting against experiments. There are some fundamental physics that is valid, that based upon the plane of symmetry or the crystal of symmetry. We will come into those. But those are the material behavior, and how do we understand the material behavior is based upon experiments. So, we do experiments, we measure the stress, we measure the strain, and we see how they are correlated in different directions. Now, there are two general requirements for this. So, the two general requirements are, first is that it should obey the laws of thermodynamics. It's very obvious. And second, it should obey or satisfy rather the condition of objectivity. So, let us define each a bit. So, first thing is that it should obey the laws of thermodynamics. There are two laws. As per the first law, whatever energy or the strain energy is being generated in terms of deformation of a body can either be stored reversibly and can be extracted later, or can be irreversibly dissipated as heat energy. Right? So, the energy needs to be conserved. And according to the second law, if a body is operated under a cyclic load and that the load or the stress is reversed back to its original condition and there is no change in the internal energy, then the work done on the body should either be positive or 0. Okay, that is according to the second law. So, the net change in entropy should be greater than or equals to 0. Alright, what is this objectivity or the condition of objectivity? The condition of objectivity states that our material frame is independent of the frame of reference. So, our material behavior or the material properties should be independent of the frame of reference. It should be same in the undeformed state and in the deformed state. Okay. With that, we will start with the most commonly used behavior, that is the linear elastic material behavior. Okay, so what is this? So, we are considering an isotropic linear elastic material. So, an isotropic linear elastic material should justify these following points. First is that the sample deforms reversibly. What I mean by reversibly is that that if you apply the stress, it will deform to a certain extent, and when you remove the stress, it should come back to its original state. So, if I pull this pen, it will deform to a certain strain, and if I release this pen, it should be able to come back to its original or initial state. That is the first consideration. Second consideration is that the strain only depends on stress. And not the loading history. So, what I mean by that is that the body does not care how many times you have loaded or unloaded the sample, how many times, at what steps the forces have been applied. It will only look at the instantaneous stress, and that instantaneous stress will give you the strain at that point. Okay, so, it does not depend upon the stress history. You can take it in one shot, you can take it in steps, you can take it with any other curved path possible. C1 is that the stress is very obvious from the linear thing. The stress is a linear function of the strain. And the last would be that the material has no characteristic orientation. So, what the last point means, and it comes from the isotropic part of our definition, is that all directions are uniform, not in terms of stress or force applied. Of course, you can apply different forces from different directions, but from a materials response perspective, all the directions are equal. Whether you apply it along the x-axis, y-axis, z-axis, or any axis in the intermediate, the materials response should be similar. So, that is the requirement for an isotropic linear elastic material. Okay. If you look at the stress strain curve for this material, say your x-axis is your strain along one direction. This is the most common experiment that you have studied in your undergraduate or maybe even in your 12th standard. So, sigma 1 is a stress being applied, and the stress strain behavior is going to be a linear line. This is something that you know, right? So, if you load a sample up and then you unload, it should be able to come back to 0. Again, if you compress the sample and then you relax, it should be again able to come back to 0. So, if the stress is relaxed, the strain will also be relaxed and it will follow a linear behavior along that line. Okay. Then let us look at the stress strain relation. For these isotropic linear elastic material. Let us first just pick up that our strain epsilon ij, and we are doing it for infinitesimal deformation. Epsilon ij is 1 by 2 del ui by del xj. Okay, and we have that all the stress measures are the same, sigma ij equals to other stress measures. All right. So, the first formula that does come to our mind is that sigma is equals to E epsilon. This was our Hooke's law, and that is something that we have studied very thoroughly in our undergraduate, right? And so, the uniaxial stress causing strain is proportional to this elastic modulus. Okay. Now, since we are doing this more from a modeling perspective in a postgraduate level, we should be able to generalize this expression and look at all directions possible. So, our stress tensor is symmetric, our strain tensor is symmetric, which means that our 9-component stress tensor and our 9-component strain tensor can be relaxed down to a 6-component vector, right. So, your sigma 1 2 is equals to sigma 2 1, sigma 1 3 is equals to sigma 3 1, and sigma 2 3 is equals to sigma 3 2. Okay, so considering that, likewise in the strain, we have epsilon 1 2 equals to epsilon 2 1, epsilon 1 3 equals to epsilon 3 1, and epsilon 2 3 is equals to epsilon 3 2. Okay, so if we relate the strain to stress, then we make a vector. Usually our elastic modulus tensor or our compliance tensor, both of them are 3 cross 3 cross 3 cross 3, which means that they have 81 components. Now, we cannot show on a piece of paper. This is a 4th dimensional matrix, right? It's not possible to draw a 4th dimensional matrix. In a computer, you can set it up, but on this paper. So, what we do is, if we have a 2 cross 2 or a 2-dimensional matrix, we make it a vector. If we have a 4-dimensional matrix, we convert it to a 2-dimensional matrix. Okay. So, epsilon 1 1, 2 2, 2 epsilon 2 3. I'll come to why I wrote down 2 over here. and say that we also have our thermal expansion. So in that case alpha delta T. So strain due to thermal expansion. Any type of expansion, whether it be thermal expansion or volumetric expansion, they are always driven in the axial direction, right? They are not in the shear direction. All right, so this is our expression for which relates strain to stress. Now, before we go to the other side, let's first write down that epsilon ij and sigma ij are symmetric tensors. That's one point. Epsilon ij by definition, our epsilon 1 2 equals to 1 by 2 del u1 by del x2 del u2 by del x1, which is equals to 1/2 of the gamma 1 2. This is our shear. If we want to relate this to our stress, then the shear stress relates to the shear strain. And this part itself is related to the sigma 1 2. So, this 1/2 term, it needs to be multiplied to this epsilon 1 2. So, although our strain tensor by definition has this 1 by 2 incorporated, we multiply a factor of 2 to the shear strain component only, not to the longitudinal or the axial stresses, right. So, only to the shear strain component we are multiplying this 2 term, so that this shear can be related, strain can be related to this shear stress. All right. We have already shown that, right, that our shear is, if this is our axis and this is our body, and this body gets deformed symmetrically about the two axes, then from both direction we have this theta, and since it is 2 theta, and that is why this 1 by 2 term comes. Okay. Likewise, we can try to set up our stress tensor. Before I do that, just write down that this is from thermal expansion. So, strain from thermal expansion. Okay. Let's write our stress sigma 1 1 2 2 sigma 1 2. This is E 1 plus nu is 2 nu 1 minus nu 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 and then we will have 1 minus 2 nu by 2 This we will multiply with our strain epsilon 1 1, epsilon 2 2, epsilon 3 3, 2 epsilon 2 3, 2 epsilon 1 3, 2 epsilon 1 2, plus we will have minus we will have the effect of the expansion alpha delta T 1 minus 2 nu. All right. So, we have our effect of our elastic loading, so our elastic strain effect, then we have a thermal stress effect or stresses due to thermal strain. All right. So, now we have so far defined stress tensor and strain tensor in the matrix format. Right. However, writing it down in terms of matrix in a piece of paper becomes difficult. We have already learned how to use the Einstein summation notation. So, we can simplify these just for the sake of writing in the piece of pen and paper. Of course, when you will do it in a software in a simulation, these will go as matrices. However, to understand or to visualize these expressions, it is easier to write them in terms of the index notation. So, in index notation, we will have epsilon ij is equals to 1 plus nu over E sigma ij minus nu over E sigma kk delta ij plus alpha delta t into delta ij. So, this is one expression. The second expression will be sigma ij will be equals to E 1 plus nu, and then we will have epsilon ij plus nu over 1 minus 2 nu epsilon kk del ij minus E alpha delta t over 1 minus 2 nu, like last time we have del ij. Okay, let us block it again. So, we have these two expressions that we have written, one our strain tensor in terms of stress tensor and our stress tensor in terms of strain tensor. We have these additional terms of alpha delta t or E alpha delta t over 1 minus 2 nu. These are from the thermal stress or the thermal strain. They are in terms of strain it is added, in terms of stress it is subtracted. Okay. So, you can always check this. Let us give a quick check. So, along sigma 1 1, epsilon 1 1 should be 1 over E into sigma 1 1 plus alpha delta t. So, we can see that epsilon 1 1 equals to 1 plus nu sigma 1 1 over E minus nu over E sigma 1 1 plus sigma 2 2 plus sigma 3 3, right, plus alpha delta t into delta ij. Okay. Again kk repeating index means summed over that index, right. So, you can sum it over that index. Let us check. So, epsilon 1 1 is sigma 1 1 minus nu sigma 2 2 minus nu sigma 3 3 and everything else is 0 plus alpha delta t. So, we will also get from here say epsilon 1 1 equals to 1 plus nu over E sigma 1 1 minus nu over E sigma 1 1 plus sigma 2 2 plus sigma 3 3. Delta ij 1 1 will be 1. If I is not equals to j, it will be 0 plus alpha delta t. So, this will be 1 over E sigma 1 1 minus sigma 2 2 minus sigma 3 3 alpha delta t. Okay, and this matches with our vector or our matrix notation. Okay. So, we now have a confident model of relating our displacements or our strain to our stress. That was the objective of the constitutive model. Okay. Now, we are writing this in a very big format. We can even further simplify this down, and we are using something called the stiffness tensor or our compliance tensor. Okay. If you are relating stress with strain, then sigma ij is equals to C I j k L epsilon k L minus alpha delta t del k L, where C I j k L is the stiffness tensor. Likewise, epsilon I j is equals to S I j k L into sigma k L plus alpha delta t into del I j, where S I j k L is the compliance tensor. There is a slight misnomer in these cases. That is how it has been written and has been used so far. So, CIJKL is stiffness tensor, SIJKL is compliance tensor, right. So, just the names have the first letters have flipped. However, that is how it is. Both of them are a 3 cross 3 cross 3 cross 3 that is having 81 components. Okay. Now, a total tensor should have an 81 components. However, due to certain properties, and we will come over it, our stiffness tensor and our compliance tensor both will have only 36 components because of certain symmetries. Okay. So, with that we can write what CIJKL is. So, CIJKL is equals to E over 2 times 1 plus nu del of IL del of Kj jk ik del of jl plus E nu over 1 plus nu 1 minus 2 nu del of ij del of kl, and our Sij kl is equals to 1 plus nu over 2e. So, inverse of this del of il, similar del of jk del of ik del of jl minus nu over e del of ij del of kl. Okay. So, this is how we can write our Cijkl and Sijkl. You can substitute these and give it a check whether it will match. Just take any one component of strain or stress as epsilon 11 or sigma 11, put these values in and you can give a check. Okay. One thing to note is that that kl are the repeating index, so they will be added over. So, it will be summation k equals to 1 to 3, summation l equals to 1 to 3. Okay. Again, in this case kl is a summed over index. So, you will add k's and you will add l's. Okay. With this we have now a definition of our stiffness and our compliance tensors. We can relate the stress to the strain. Then we will look into some reduced order models. Now, we have been doing everything in 3 dimensions, so the equations becomes very cumbersome. You have a lot of terms to consider, right? There are 6 stresses and 6 strains, and we are relating all of them with a 6 cross 6 matrix of material properties. Let us bring it down to one dimensional lower, and we are looking at a planar body. In 2 dimensions. The first thing that we will talk about is plane strain. So, plane strain model, as the name suggests, we consider that the strains are limited only in the 1-2 plane or the xy plane, and there is no strain in the third direction, which means that epsilon 3 and anything related to 3, epsilon 1 3 and epsilon 2 3 will be equals to 0. Also, sigma 1 3 and sigma 2 3 will be equal to 0, because epsilon 1 3 and epsilon 2 3 are 0. So, sigma 1 3 and sigma 2 3 is 0. However, although epsilon 3 3 is equals to 0, that does not mean that sigma 3 3 will be 0. So, you can assume that this pen, any central section of this pen, now you are deforming this body. So, you are deforming in such a way that it is not allowed to strain in the third direction. Say this is 3 and this is 1 and 2. Right. So, this is 1, this is 2 and this is the third direction. So, you are applying forces along these axes in such a way that this body is not allowed to strain. You are holding these 2 top surface and it is not allowed to strain in the third direction. To prevent it from straining in the third direction, for example, if you are squishing it very tightly from all sides, then this length is going to elongate, right. How would you prevent this elongation? If you hold it from top and bottom like this, in that case, you will have a compressive load on the body which will prevent that elongation. So, you will have a sigma 3 3 to counter the strain development naturally and the natural strain development in the epsilon 3 3 direction. Okay. So, you will have sigma 3 3, but you will not have epsilon 3 3. And at the same time, there will be no shear in the third direction and no shear strain in the third direction. So, our expressions will be, now we will have just 3 terms, sigma 1 epsilon 1 1, epsilon 2 2 and 2 epsilon 1 2 equals to 1 plus nu over E, 1 minus nu 0 minus nu 1 minus nu 0 0 0 2, sigma 1 1, sigma 2 2, sigma 1 2. And if there is any thermal consideration, so thermal strain alpha delta T 1 1 0. Likewise, our stress matrix sigma 1 1, sigma 2 2, sigma 1 2 equals to E over 1 plus nu 1 minus 2 nu 1 minus nu nu 0, nu 1 minus nu 0, 0, 0, 1 minus 2 nu 2. Two epsilon 1 2. Please remember to write this 2 with epsilon 1 2 minus E alpha delta t one 1 0. Okay, so this is what we have. Our sigma 3 3, we need to write it separately, is E nu epsilon 1 1 plus epsilon 2 2 divided by 1 minus 2 nu 1 plus nu plus E alpha delta t over 1 minus 2 nu. Okay, because we cannot express this third term in this matrix, so sigma 3 3 is found out separately, and then this matrix exists. Right. We can write this in terms of index again. So I am, instead of using ij, because we have used ij for 1 2 3, and to keep it slightly different from the general, from the full linear elastic model, let us use alpha beta instead of ij. Okay, so epsilon alpha beta 1 plus nu over E sigma alpha beta minus nu sigma gamma gamma delta alpha beta, just like last time, plus 1 plus nu alpha delta t delta of alpha beta, and sigma alpha beta will be equals to E over 1 plus nu epsilon alpha beta plus nu over 1 minus 2 nu epsilon gamma gamma delta alpha beta minus E alpha delta t over 1 minus 2 nu of del alpha beta. Okay, so this is our stress strain relation for the plane strain condition. Again, where here alpha and beta can be 1 or 2. So both can be 1 or 2. Now with this expression in mind, we are able to express all of this. Sigma 3 3 is found separately, right? So we are just expressing this matrix in terms of this index notation. Sigma 3 3, you find it out separately using this formula. Okay, where is this plane strain applicable? It is applicable for a body with a long E3 direction compared to E1 and E2 in the mid plane segment. So if you take out a plane, say this body, it has a smaller E1 and E2 and it has a longer E3. If you take out a segment from the mid plane, in that case the strain in the third direction can be ignored because E3 is very large compared to E1 and E2, and then this plane strain application can be used. So whenever you use a model, say in COMSOL or in ANSYS or in some software, some program, even in Abacus, you have an option to select, if you are doing planar analysis, whether you have an option to select whether it is a plane stress or plane strain. There is a reason they are giving you that option. It is an approximation of a 3-dimensional condition, and you are ignoring the third dimension based on certain assumption. That assumption in the case of plane strain is that it is not allowed to deform in the third direction. However, in the case of plane stress, it is allowed to deform in the third direction. However, the stresses are limited to the 2-dimension. Okay, so the second one is our plane stress. Let's write model over here. So in the plane stress model, what we have is that sigma 3 3 equals to sigma 1 3 equals to sigma 2 3. Any stress in the third direction is 0, and consequently epsilon 1 3 equals to epsilon 2 3 equals to 0. However, if the body is allowed to only apply stress in the x direction and there is no stress in the y direction, where the body can deform in the y direction, in the z direction, the third direction. So even if you are applying stress along 1 and 2, the body is allowed to deform in the third direction. Okay, then let's quickly write our expressions. Epsilon 1 1, epsilon 2 2, 2 epsilon 1 2 is equals to 1 over E 1 minus nu 0 minus nu 1 0 0 0 2 1 plus nu, sigma 1 1 sigma 2 2 sigma 1 2 plus alpha delta t 1 1 0. Likewise, sigma 1 1 sigma 2 2 sigma 1 2 is equals to E over 1 minus nu square. We have 1 nu 0, nu 1 0, 0 0, 1 minus nu over 2, epsilon 1 1, epsilon 2 2, 2 epsilon 1 2 minus E alpha delta t over 1 minus 2 nu 1 1 0. Okay. Now, the strain in the third direction epsilon 3 3 will be equals to minus nu over E sigma 1 1 plus sigma 2 2 plus alpha delta t. Okay. You can also express this in terms of alpha and beta. Please refer to again to the Alan Bauer's book, and you will be able to find the definitions in terms of these index notations in alpha and beta. Okay. There are some other elastic constants which we also commonly use. So far we have been introduced with two constants, E and nu. These are the only two constants in the case of an isotropic linear elastic body. So where E is the elastic modulus and the nu is the Poisson's ratio. Using these two values, we can find out some other material properties. For example, the bulk modulus K is equals to E over 3 1 minus nu. It relates the bulk and the hydrostatic stress to the volumetric strain. And we have a shear modulus used by mu, sometimes people use G, is E over 2 1 plus nu, and then we have our Lame modulus. So, lambda, this will be our nu times E divided by 1 plus nu, 1 minus 2 nu. We will show a better explanation of how the shear modulus and Lame modulus can be used. I can quickly show you where the shear modulus is used. So, if you see over here, there is 2 1 plus nu over E, and that is our shear modulus. Okay, so this 2 1 plus nu over E, inverse of this is our shear modulus. So that is where we can use some of these terms. Now, our strain, the total strain is actually a summation of our elastic strain and our thermal strain. This has been very obvious so far, right? We have been adding this alpha delta t term separately to our sigma ij Cij KL term. So this thermal strain is alpha delta t into delta ij. This elastic strain can be defined as 1 plus nu over E sigma ij minus nu sigma kk to delta ij. Okay. If that is the case, then we can find out what is the strain energy. So, the strain energy of a body can be defined as given by U is 1/2 of the product, that is, we are talking about tensor double dot products, right. So, sigma ij, epsilon ij, but only the E term, that is our elastic part of our strain tensor. So, it is 1/2 sigma ij E ij. In terms of just sigma ij, it is 1 plus nu over 2E sigma kk sigma jj. In terms of strain, it is E over 2 1 plus nu epsilon ij. Again, this is a double dot product, so you are just adding up all components multiplied, sigma 1 1 square plus sigma 2 2 square, sigma 3 3 square, 1 2 square, 2 2 square, 2 3 square, and so on, plus E nu over 2 1 plus nu 1 minus 2 nu of II of kk. Okay. We can also say from here that epsilon E ij equals to del u by del sigma ij, that is the derivative of the strain energy with respect to our stress, and sigma ij equals to del u over del epsilon of ij in the elastic part. Okay, so we can end up today's lecture. I would like to go over a little bit more on this topic of general anisotropic linear elastic material. So apart from this isotropic materials that we have talked about so far, there are other materials which does not have to be cubic, does not have to be isotropic. So we can have orthotropic materials, we can have cubic materials and other crystal lattice. Their elastic constant, that is their stiffness tensor or the compliance tensor, is going to be different. So in the next lecture we will quickly wrap up over these general linear elastic materials and also some generalized expression of the Hooke's law, and we will go into developing the Navier's equation. Now we have all the tools required. We have the strain related to deformation, we have the stress related to forces, we have a governing equation which relates the stress to the strain, and we just need to replace that stress term with the strain term. So we have worked over the constitutive models which we can replace, and we will have a final model or a final expression ready which we will use to model our expressions, right? So we will also look at plane stress and plane strain condition. Plane stress is mostly used for thin membranes, and the plane strain for bigger blocks from the central plane direction. So I'd like to thank you for your attention for today's lecture, and we will meet in the next lecture. Thank you.